Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, thanks for coming. I'm Madan Muswati from the Research and Software Engineering Group, and it's my great pleasure to invite Gray here today. Gray is a Truman Fellow at the Sandia National Labs, and he's been interested both in the theory and practice of linear algebra algorithms, high-performance computing, and he's going to be talking about some of his work on how do we do on fast matrix multiplication, how we can avoid communication. It's an interesting new direction for optimizing very important algorithms. His work he's received a lot of awards for his work, and some of which are, I'm just going to look at them. Like he's received the Siam Linear Algebra Prize and 2 conference best paper awards. And his thesis actually received a honorable mention at the ACM Doctoral Dissertation Award. And he also received the C.V. Ramamurthy Distinguished Researcher Award at UC Berkeley. So Gray?
Thank you very much. Thanks for the introduction, the invitation. I'm happy to be here. So the title of my talk, Communication Avoiding Algorithms and Fast Matrix Multiplication. I'm going to sort of address those 2 things in order. And I'll start with a little bit of an overview of what I mean by communication avoiding. Talk about sort of the theory and practice for the state-of-the-art in linear algebra. And then talk about how Strasson's matrix multiplication and thinking about that from the perspective of communication sort of led me into studying fast matrix multiply, sort of trying to do better than Strassen, both in theory and practice. Okay, so I'll start with talking about communication costs. So the first idea is that if we care about performance of our code, we can't just think about how many computational operations we're doing. We've got to worry about communication. So what I mean by communication is on a sequential computer, it's moving data up and down the memory hierarchy. So you can think about DRAM and cache. And on a parallel computer, I'm talking more about messages. So if you're on a distributed memory architecture, you're using something like MPI, you're passing physical messages. And the point is, if you want to do analysis of your algorithm to figure out how much time it's going to take, keeping up with the computation isn't enough. Okay, so here are the pictures of the memory models we need to start keeping up with communication. And so they're these simple block models that are simple enough that we can do sort of high-level analysis of our algorithms, but they match the architectures well enough that they tell us something useful in practice too. Okay, so to look at our runtime model, which includes both computation and communication, we keep up with computation in the usual way, flops or arithmetic operations in general. And then for communication, we'll keep track of how many words do you send. So a word might be an int or a floating point number or whatever the relevant unit is for the algorithm. So to get a high-level sort of first-order runtime picture, we could just add the 2 terms. So how many computational operations do you do times the time per flop? How many communication operations do you do times the time per word? And when we get high-performance implementations, we really want to overlap these 2 things, try to overlap computation and communication. But to first order, we're just going to add these 2 terms. And when we care about asymptotics, we haven't made any mistakes. The big takeaway is that the cost, this beta term, is a lot bigger than the gamma term. So we're getting into a regime where flops are almost free, and really what we should be focusing on is just this second term. Okay. The beta term being bigger, or beta being bigger than gamma, is most people sort of understand that in terms of time. I think that's pretty accepted, but it's also true in terms of energy. So let me just put some numbers to this. The different rates we can compare. So on the left is the improvement per year in the flop rate, and more recently this has come because of multi-core and not Moore's law. But in these next 2 columns are measures of bandwidth, both on a sequential machine with vertical data movement, and on the right, this is on a distributed memory machine with horizontal data movement. So everything is getting better over time. but the rate at which flops are getting better is a lot faster than the rate at which communication costs are. Sure.
So these algorithms are not sensitive to latency?
So I've sort of left latency off. Many of them are. I just sort of, to simplify, I've only worried about bandwidth costs. But yeah, so to get a better picture, we keep up with latency as well. For matrix multiplication, that I'll sort of focus on in this talk, it's usually not an issue. It's usually just bandwidth and computation. Okay, so these are the improvements in time. So if you care only about time, you need to worry about communication. But as energy costs are becoming more and more important, we can look at how these things compare. So this is some data from sort of the exascale thrust. And so the blue curve is how things are now, and the red curve is sort of extrapolated to exascale. But the big takeaway, so this is the y-axis is a measure of energy, and these are different operations you might do. And the big takeaway is that these operations, so this is a double precision flop, and these guys are moving data on the chip, and these guys are moving data across the network. And there's orders of magnitude, so this is on log scale, of the amount of energy you use to move data off the chip. So if you want to reduce energy costs, then do as much as you can with the data you have on the node. Okay, so not just time, but also energy. The costs of communication are outweighing the cost of computation. Okay, so this is why we avoid it. And so with this in mind, you sort of look at the computations you care about, and you say, okay, can we do anything better? If this is our bottleneck, can we do anything better? And the standard way is to say, okay, well, how well can we do, and how well are we doing right now, and can we improve things? Can we come up with better algorithms or not? And so as I mentioned before, so we can't just worry about computational complexity. We've got to worry about the communication complexity. And sort of for looking at both better algorithms and tighter lower bounds, a lot has been done for regular computation. So things like matrix multiply, which I'll talk a lot about today, but FFT sorting and even some sparse matrix vector products, stencil operations. There's a lot known. There's a lot of theory around how good we can do and how good we're currently doing. We get to irregular computation, things that are more sort of data dependent. It gets harder, but there's ongoing work on that. Okay, all right. So this is the basic approach we want to take with our computations and the high-level analysis. And so now I want to get into some of the linear algebra algorithms. So we'll start with matrix multiply because a lot has been known for a while about this. Okay, so assume we're doing the classical algorithm. So we're going to do order n cube flops for dimension n matrices, and we're on this sequential machine. Then in 1981, it was proved this is the number of words that you have to send to do your matrix multiply. So again, n cubed is the number of flops we're doing. M is the size of this small memory where we do the operations. Okay, so that's the relationship between computational operations flops and communication operations or moving words. And then later, a little bit more recently, we have another lower bound for the parallel case. So it looks similar. P here is the number of processors you have, and now M is the size of the local memory. But it's sort of like if the one processor does n cubed over P flops, then the ratio of flops to words moved is the same. It's the square root of the memory size. Okay, so that's the important ratio here. So these are lower bounds, and in fact, there are optimal algorithms that attain them. Okay, so for classical matrix multiply, at least in theory, the communication is sort of a closed book. So we have tight lower bounds and algorithms. Okay, so the result we had a couple years ago that we were very excited about is that this result it's not just for matrix multiply that this ratio holds. So if you're doing anything that I'll say smells like three nested loops, and I'm thinking of you can write matrix multiply with three nested loops of code, and you can do a lot of direct linear algebra the same way. So if it looks enough like matrix multiply, I'll say very concretely, then we get this relationship. So the number of words you send is related to the number of flops you do, and the ratio depends on the size of the memory. It's the square root of the memory size. It doesn't matter if your matrices are dense or sparse. It matters how many flops you do. And this bound holds for both sequential and parallel.
So I'm assuming that the operations that you're doing within the loop have some properties like associativity, commutative. I mean, are you relying on that you're doing multiplication and addition in some similar?
No, not really, actually.
No.
So this is not taking into account dependencies you need or anything like that. I mean, there's So there are limits to how you can restructure the code. For example, if you use Strassen's ideas, then this breaks down. But I mean, so everything we've looked at with linear algebra, you have this associativity and commutativity. And so this sort of says, however you use those properties, you can't beat this bound. So, in whatever order you do the dot product is free, but this bound will hold.
Doesn't that number of flops, though, the numerator, isn't there some characterization of the distinct number of memory locations you're touching there? Because I can just touch the same memory location over and over again. I can have as many flops as I want. So I don't quite understand how the numerator is relating to memory.
Sure. Right. So if you redo the same flop over and over again, then this won't hold. We have to assume those things away.
In the previous slide, matrix multiplication used three-nested loops, but you had I'm trying to see how the lower part of that slide relates to the theorem, because the number of processor P is part of.
Right. So this next theorem is per processor. There exists some processor who has to. I'm sorry. Every processor has to. However many flops that processor does, the number of words that it must read or write from other processors is given by this. So if we look to
must communicate. Okay. It must be communicated, as opposed to they all communicate.
Right. So that's an important distinction. So this is more related to the runtime. I mean, so if we don't care so much about the total communication done by all processors, we care about the max, the slowest processor. So some processor must do this much. And so that processor, I mean, some processors must do n cubed over p flops. That's how the argument goes.
So the square m is just the memory on the local machine, on one machine?
On one node,
yes.
Yeah. So, I mean, I'm sorry I haven't been specific enough in this theorem. I mean, the important relationship is that you have your flops are sort of embedded in a three-dimensional object, and the arrays they're accessing are two-dimensional objects. That's sort of the key here. If you change that, then you get some different functions. But all of linear algebra sort of has this relationship where the iteration space lives in 3 dimensions, and the data that you're accessing lives in 2 dimensions. Okay.
So have you looked at some other clustering algorithms like k-means? They also have 3 nested loops, but I'm not sure if they.
So I haven't looked at k-means. I'm not sure. So there's been other folks at UC Berkeley who have worked on where the number of loops changes, and so there are really nice generalizations of this. So, for example, if your data lives in 1 dimension and your iteration space in 2 dimensions, you get a different answer. And so they have a very generalized form of this theorem. I'll just focus on this one for linear algebra. But I'm not sure that they've looked at k-means either. Okay, so in the context of linear algebra, this is like if you're doing direct linear algebra, you're not doing iterative linear algebra, then this theorem will apply. So like the BLAS, the basic linear algebra subroutines, these are ways of solving linear systems for different matrices, solving least squares problems and eigenvalue computations. And then some of it, if the graph algorithms work enough like linear algebra, it applies to those too. Okay, so the reason this is exciting is because all these computations, they're in libraries, they're very important, lots of people use them, and now we have this lower bound that says this is the best you can do. So the natural question is, okay, well, are the standard algorithms that everyone's using, are they reaching this lower bound? And sure.
Triangular solve also?
Yeah, so that lives in, if you do triangular solve with multiple right-hand sides, that's a BLAS 3 operation. Yeah, if you do, so this actually applies to triangle solve with 1 right-hand side, but you'll never attain it. It's not a tight bound in that case. But for BLAS 3, then it's a tight bound. Okay, so we can start to compare and see when it's tight and when it's not. And so I'll just give you a table of some of the optimal algorithms. And just by sort of looking at the dates and the references, you can see that some of these algorithms are quite old. So we just look at them, do the analysis, and say, okay, it's reaching the lower bound. This is the best we can do in theory. We need to go tune these algorithms now. But some of them, the references that have more recent years, there have been recent improvements. So we looked at the standard algorithm, the one that exists in the library that everyone uses, and say, okay, it's not optimal, can we improve it? And in some cases it was straightforward, in some cases it was quite complicated. But we can have this nice, we can look at these important problems and see, is there a gap, can we close the gap? So this is the story for sequential machines. We have sort of a similar, a little bit more complicated story for the parallel case.
So does the proof of your lower bound, does it hint at a better algorithm? Or like in each of these improvements, was it like a template that you applied to come up with a specific algorithm and you actually had, or was it completely different?
So no, in this case, the lower bound didn't help very much. So in particular, the lower bound ignores dependencies. So in matrix multiply, you have very few dependencies. You can do the scalar multiplies in any order you want. And for this stuff, there are lots of dependencies. And so, I mean, some of these, the numerical properties even change. So you got to make sure that the changes you're doing aren't going to create stability issues. So for example, for LU decomposition, so the standard way is doing partial pivoting. And with partial pivoting, it doesn't seem likely that we can reach the lower bound in terms of latency, in fact. This paper here from 2011, they generated a new technique for pivoting. So it's different than partial pivoting. It's as stable in a certain sense, but it's different. So the numerical properties change. So it's much more sort of particular to the different operations, getting the better algorithm. I think. Maybe, so I'll get to Strassen's matrix multiply soon. I think there the lower bound helps a little bit more. Okay, so let me give you just a couple examples. So that was this slide is sort of all theory of reaching the lower bound in theory, sort of ignoring all constants. And so just to give you a few examples, I wanted to convince you that this does translate to better implementations in practice. So just to flash some speed ups for different computations. So things like if you're solving the symmetric eigenproblem for band matrices, the dependencies are really hairy and messy. But if you're careful about the communication costs, you can get good speedups. Computing QR decomposition has maybe been the most useful new algorithm because it comes up in so many contexts, and so we've gotten speedups on different architectures there. So it's not just theory. This stuff does translate into practically good implementations. Okay, so from there, I want to sort of transition to talking about Strassen's matrix multiply in particular, and sort of how that leads into my more recent work. Okay, so here's Strassen's algorithm, in case you don't have it memorized. So the clever idea is that if you're doing 2x2 matrix multiply, you need only 7 scalar multiplies and not 8. Okay, so you take these combinations of elements in the left input matrix and combinations of elements in the right, and you do these 7 multiplies, and you take these weirder combinations, and you get out your output elements. Okay, so we can write the classical algorithm in a very similar way, and here you see this the 8 multiplies, a lot simpler expressions here. So 8 multiplies and 4 additions, 7 multiplies, and turns out to be 18 additions here. Okay, so this is what you do if you have to multiply 2x2 matrices. Why is this nice? We can use the idea recursively. Okay, so instead of 2x2 matrices, if we have n by n, we just split our matrices into quadrants and then run this algorithm and call Strassen recursively. Okay, so how many flops do? We write down the recurrence. Base case, let's say we go all the way down to 1. We get a number of flops, which is not n cubed, but into the log base 2 of 7. Okay, so now we're at 2.81 for our exponent. So this is a big improvement. This is an improvement in the exponent, and that's why it's an exciting idea. Okay, but I said that we can't just do computational analysis to figure out if this is a good algorithm. We've got to look at the communication cost. So what is the communication cost if you run this algorithm on a sequential machine? So I'll just change the recurrence down here. This line stayed the same. We changed the base case. This is when things fit into cache. And now we get a different expression down here, and this is the word count on a sequential machine. So I've written it in sort of an unsimplified way. So it looks complicated, but there's a reason for that. So I want to compare it to the classical algorithm. Okay, so here... Sure.
Can you explain the first recurrence?
This line?
Yeah.
So this is the same actually as the flop recurrence. So here's the flop recurrence. We're going to do 7 subproblems with half the size. And all these guys are matrix additions and subtractions. So that's order n squared flops. And when we go to words, it's actually the same thing. Because when we add two matrices, we've got to just stream through them. And so this is order n squared words as well.
And so there you're assuming that there's no sharing between the 7 subcomputations.
It doesn't, I mean,
No, when you
it
do
doesn't matter.
has-
This might change the constant there.
Okay.
I mean, this 7 is the number of multiplies we do. And so that, I mean, that's important. But yeah, I mean, for the additions, there's some constant there. Maybe they're sharing, maybe there's not.
Okay.
Okay, but changing the base case, so now if we don't go all the way down to 1, we go to when n is smaller than square root m, that means our problem fits in cache, then we just have to read and write the problem. Okay, so we get this weird expression. And so let me compare it to the classical algorithm. Okay, so this slide will get a little complicated. So let me explain how the table works. So this column is all classical, and this column is all Strassen. The first row is on a sequential machine, and the next 2 rows will correspond to the parallel. Everything, all the units here are words. So in parallel, I'm talking about the max words over all processor, and in sequential, it's just words moving, say, in and out of cache. I'll use asymptotic notation here. So big O is the upper bound. That means if this is true, if we have a big O, that means an algorithm exists. The lower bound is the big omega. That means we have a lower bound. And then I'll write theta if we have matching upper and lower bounds. Okay, and then in matrix dimension, m is the size of the fast memory or the local memory, depending on sequential parallel. And then p is the processors. Okay, so the analysis we had on the previous slide gave us an algorithm. So we got a big O with this expression. And I've written it this way so we can compare to the classical algorithm. So you see that log base 2 of 7 replaces 3 over there. So this guy is smaller than that guy. Okay, so we saw that in the computational cost. We've reduced the computation in the exponent. This is a big improvement. We've also reduced the exponent in the communication cost. Okay, so that was the first exciting thing. I mean, usually you have to do a trade-off of computation communication, and here it's a win-win. So that got us excited. But I mean, this is just one way to write down Strassen's algorithm. Can we do anything to reduce the communication of Strassen's algorithm? And so after a lot of work and a lower bound that took on a very different form, at least the proof did, we were able to prove that this big O is actually theta. So we proved a lower bound that say that this algorithm is tight. So writing it down in the usual recursive way, that's the best thing to do. Okay, so that was nice. So now we have no gap. And the other thing that's nice is the lower bound didn't care if you were on a sequential machine or a parallel machine. So we got a very similar bound in the parallel case. Basically, divide that guy by p. Okay, so we've got a lower bound, and then let's compare it to the classical. So here we have matching lower and upper bound, and again, the difference is in the exponent. Okay, so similar story for comparing classical and Strassens in sequential and in parallel. Okay, so we had this lower bound, but we weren't sure if an upper bound exists. So we looked in literature because people had tried to parallelize Strassen before, and it turns out that they weren't optimal. So they had some ideas for parallelizing it, and they weren't reaching this lower bound. And so we said, okay, well, let's see if we can come up with a better algorithm. And we could, and it was a lot of work, but I'll just signify it by changing the omega to a theta, and we have a tight bound there. Okay, so that was great. We matched the lower bound. We had an optimal algorithm, but there was actually an extra term that showed up in our analysis. And so it's kind of hard to compare these two terms. This guy can actually dominate in some cases. So we looked at this term and we said, okay, so now maybe our upper bound isn't always tight. Let's compare it to the classical case. And it turns out the classical case has a similar term that shows up, and there's a lower bound and upper bound for this guy. So okay, this term is necessary in the classical case. It's probably necessary in the Strassen case. So we worked to get a lower bound, and we got it. And so we have a theta.
That's happening because your matrix can fit in memory. Is that for small matrices? Is that the intuition?
I'm not sure if I have good intuition for what happened. I mean, so this term only matters when you scale out to lots and lots of processors. And then you're never really constrained by memory. So if you have a fixed problem size and you scale out the number of processors, you sort of get more memory as you scale out those processors. And so at some point, your memory is never an issue. And so when you think about taking, so if you simplify this, m ends up in the denominator. And take your memory to infinity. And then this guy just dies away. So if you had infinite memory, this is the only thing that bounds your communication. Yeah, I'm not sure if that gives good intuition. But But we saw the term first as an upper bound, worked hard to get the lower bound to make it tight. Okay, so then we felt good about this. This is matching upper and lower bounds for both classical and Strassen's algorithm. Okay, so again, just to show you this is not only theory, here's some performance results when we implement this and put it on a big machine. So here's a strong scaling plot. So we're increasing processors along the x-axis, and this is a measure of performance on the y-axis, and it's effective gigaflops. So we're comparing this, sort of assuming that everyone does order n cubed flops, which is not fair, but you can think of this as inverse time. So the speed up will make sense. Okay, so this black curve is basically the library code for the classical algorithm. I told you there was an optimal algorithm in the classical case. If you implement that, you get the green line. These blue lines were the old ways that we found in literature for parallelizing Strassen that didn't meet the communication lower bound, and then the red curve is our algorithm. So it's outperforming, and it's like a almost a factor of 2 at the best spots. And speeding, this line signifies machine peak for any classical algorithm. So if communication were free or for a classical algorithm, it still can't beat that dotted line there. Okay, this is a really big problem. 94,000 by 94,000 matrices. And most of the time, except at the very right end of the plot, is computation. So the big win, the reason the red curve beats the green curve here, is more computation than communication. But we have a win in both areas, and so we wanted to test sort of when things are communication bound, how do things compare? So we looked at a smaller problem. So this is less than 5,000 by 5,000. And we scaled it out to a bunch of processors. And now I've flipped it. So now this is execution time. So now down is good, and note it's a log scale. Okay, so here's the library code. And basically when the curve starts going up, that means you start to use more time with more processors. So you're not scaling at all. You're not even close to strong scaling. You're not scaling. And if you use the optimal classical algorithm, then you can scale farther. But Strassen lets you scale even farther and get better performance. So here, I mean, the local computation is very little. This is a communication-bound problem. And we see the win here because of this nice property of Strassen's algorithm of requiring less communication. Okay, so that's just to say, not just theory. This is also a good idea in practice. Okay, so let's go back to the theory slide. So the story is almost done for Strassen's algorithm. I mean, at least in theory, we have everything tight. Implementation, I think, can be much improved. But the exciting thing is our lower bound and also our ideas for the algorithm aren't particular to Strassen. So if you take basically any fast matrix multiply algorithm and say the exponent you get with this fast algorithm is omega naught, then the communication costs just change log base 2 of 7 to omega naught. So if you get a better algorithm in terms of flops than Strassen, you get a better algorithm in terms of communication as well. And we have a way to parallelize it, and we have tight lower and upper bounds. So this is quite exciting to us because people have beaten Strassen before. And so let's just plug in their algorithm and see the speedups. So people have worked on this since Strassen came up with his idea in '69. And again, when I say fast algorithms, I mean omega naught is smaller than 3, and we hope smaller than 2.81, which is Strassen's exponent. And there's lots of improvements over Strassen. So this is a plot, these are years. So from 1969, when Strassen came up with his idea, to the present, of how the bound on the exponent of matrix multiply has improved. So here's Strassen 1969. There was a little improvement here, and then a big jump. And these are I've just sort of cherry-picked some good references. There are a bunch of dots in between. And now the world record is 2.373.
Is this still for general matrix?
Yes.
Not special cases.
Not special cases, no. There's some caveats which I'll get to.
Okay.
So like Strassen got back from retirement.
Yes. Lots of people beat Strassen, even Strassen beat Strassen. Yeah.
Is it the same Strassen?
Same Strassen, oh yeah. Yeah. And so I sort of picked these names. So there was his idea. This is Dario Bini. This was one of the reasons. So these guys built on him. Strassen built on Schoenhager's idea, and Coppersmith-Winograd sort of puts those things together. And this is Virginia Williams. A year or two ago, she came up with the improvement over Coppersmith-Winograd, and she used all the same ideas. Just sort of took their ideas a little further. This looks pretty flat because it is pretty flat. This is 373 here. This is 376. So a tiny improvement, but people are very excited about it.
People are excited.
Very excited about it.
Great.
I mean, you know, lots of people have worked hard on this problem. Okay, so why don't we just plug in this algorithm and see how we do on a supercomputer? Okay, we can't do that for a number of reasons. So pretty much all of this is just theory. And a couple big reasons are, one is that an important idea, the one that Bini came up with, is that you don't have to compute matrix multiply exactly. You can use an idea of an approximation. So you compute A times B, but your output is the right answer C plus a little error. And your algorithm has this parameter lambda in it that as you send it to 0, then you get an exact algorithm. Okay, so it turns out that if you have a scheme for doing this, then you can get an exact algorithm out with only a log factor overhead. And to theoreticians, that's fine. You just make it a tilde O instead of an O, and you're done. The other problem is that a lot of these algorithms aren't explicit algorithms. No one's written them down because they don't care to. But they prove that there exists an algorithm that yields this bound on the exponent. Okay, so particularly, I mean, so Virginia Williams sort of thinks that her approach is constructive, and it might be, but I think it'd be a lot of work and it'd be a big algorithm to write down. And it's, sure.
Everybody below, Bini and below, they use this approximate.
Yes. But I mean, I left out, there are some points sort of in this area that don't use that. And I should say that Bini's algorithm is really simple to write down. So this is an explicit algorithm. These guys are not explicit. Okay, the other thing that most people think is the main problem, and it is a problem, is that no one cares about constants here. And no one's figured out what the constant is, but for at least down here, it's got to be large. Okay, so that's going to get in the way. All right, so we can't just put in these other algorithms. Okay, so sure.
So I don't understand this. You're saying that people care about 3,000th, the difference of 3,000ths in this exponent, but there's no algorithm that actually gives you that 3,000th. So why do they care? Is it sort of like the pureness of math that we can make this?
I think so.
Wow, okay, that's amazing.
And I think more importantly, people have not been able to come up with a lower bound.
Right,
so
right.
Since they know.
So every time you make an advance.
So people, I think the best lower bound we have is quadratic.
Right.
In the sense, we know that we need at least quadratic.
Least, right, I see.
So in the sense, like there's still a big gap between 2 and 2.373. So it's very important to close the gap.
Okay.
And it's such a fundamental problem and easy to state. It's very attractive to work on. I mean, I think this is cool.
You don't have to implement the result. Right?
Yes. Okay, so the goal is now become, how do we implement? How do we find something that's on this chart but is practical? Okay, so the techniques that these folks used have been really theoretical, but can we use some practical techniques to find algorithms that maybe some of these folks have overlooked because they didn't give a great exponent? Sure.
So I mean, you're showing the path to the lowest exponent and the theoretical result. Isn't there an equivalent one of the implementable algorithms? You'd think that people would be pushing down on that as well, right?
Well, that goes basically to here.
Really? It just stops.
Mm-hmm.
So no one's been able to do better? Is that, I mean, even trying? Because you'd assume that there'd be a practical, motivation to do it, right?
Absolutely. So I'll show you that we've done a little better.
Okay. Wow. Well, congratulations.
Thanks.
But I think you're being modest here, right? So in the sense, nobody even came down to Strassen before you. Right?
I mean, people have implemented Strassen before and shown that it's practical.
Okay.
I'm arguing that we got better performance for Strassen in distributed memory. And so we did better than people had done before. But people had the idea that Strassen was practical a while ago, and they worked with it. It's just, so things got complicated here. Sort of the theory to make these jumps, I think, is hard to understand for people who are interested in coding these things. It's just a big divide. Okay, all right, so here's the effort to bridge the divide a little bit. Okay, again, Strassen's algorithm is practical, and most people think so. I mean, it's not used enough in practice for various reasons, but you can get good performance with it. So we saw that many are better in theory, are any better in practice. Can we find any ones that maybe people have overlooked? So maybe the exponent's not that much better, but they could be practically better. And then, if we have an idea that they're practical, can we implement and benchmark and show that we get a speed up? Okay, so that's what we'll go for now. So So all these fast algorithms are based on recursion. So Strassen is based on solving the base case of 2 by 2, and we use recursion, breaking the matrices into quadrants. So why don't we just solve this 2 by 2 problem, and instead of doing 7 multiplies, do 6 multiplies. So if we could solve this tiny problem with 6 scalar multiplies, and we get an exponent that's 2.58. And if we could do that, it would be practical. The problem is, so we can't do that, right? So people have proved theoretically that you cannot do six multiplies, even if you sort of relax yourself to approximate algorithms. Okay, but we're not stuck with this breaking things into quadrants. We can use different base cases. So we could break things in by factors of 3. And so now we've got a problem where there's a little more open ground. So if you do the classical algorithm, you do 27 multiplies for this one. We know how to do using 23 multiplies, and we get a better exponent. It's not quite as good as Strassen's. We don't know if there exists, say, 21, which would give you a better exponent than Strassen's. We actually don't know if there exists a rank 19 algorithm here. So that's open. So this is kind of what attracted me. It feels like this is a practical algorithm. If we could get any of these, they'd be better than Strassen's. So I'll tell you now that I haven't found. I don't know. I only know of this one. But we don't have to only look at 3 by 3 by 3 base cases. We can look more generally. Okay, so this problem boils down. You can think about it in many ways. The way I've been thinking about it is as a tensor decomposition problem. Okay, so we've got this tensor which has 3 modes, so 3 dimensions, and we want a low-rank decomposition. So these guys are like outer products of vectors, but now we've got 3 outer products. So this little chicken foot thing is a rank 1 tensor. And if we sum up these rank 1 tensors to get that, we have a rank R decomposition of that tensor. Okay, so this is basically the problem we want to solve, and there's different ways to go about it. Let me just note that the size of this tensor and say the rank that we're looking for, so that grows as the base case we're looking for grows. All right, so let me tell you a little bit more about where these sort of structures come from. So this tensor is the matrix multiplied tensor. So let's think about matrix multiply as a tensor operation. So I've got my input matrices, A and B, and let me just stack them as vectors, like this. And I want a tensor, and I'm using some sort of funny tensor notation here. So my tensor T, this is my matrix multiply tensor, I want such that this operation gives me exactly the output I want for any given inputs. Okay, and so thinking about this sort of geometrically, if I take my A matrix and I do dot products with every stand-up pencil in this tensor, that will give me a matrix out. And then I do dot products in this direction with every row in that matrix, I'll get something that has still 1 dimension left. So if I plug in A and B here, this tensor I want, and the tensor operation to put out C here. Okay, so basically the tensor is defined by the base case, and it turns out to be this really sparse tensor. So there's 4 slices, for 2 by 2 matrix multiply, there's 4 slices to this tensor, and this is what these 4 slices look like. Okay, so this is, we can express any bilinear operation this way, as this tensor operation. And so I'll just point out that the entries in the tensor, so first of all, the tensor is sparse, and second, all its non-zero entries are 1s. So it's kind of a simple guy. Okay, so that's the tensor, and so what does the sort of low rank representation of this tensor mean? So the left-hand side, I've sort of given you an idea where that comes from. So what is the right-hand side? So that's more funny notation, but for every R, that's like one of the chicken feet guys, a rank 1 tensor. So Strassen's algorithm is encoded by these 3 matrices. So if I take, for a given R, say R is 3, that corresponds to 3 vectors that I'll take this outer product of. So U3, I'm just going to put in the matrix here, U4, I'm going to put, and just stack them all together. So I'll use these 3 matrices to represent the right-hand side of the equation. Okay, so Strassen's algorithm has pluses and minuses in it, and you sort of see things pop up there. That's kind of where the right-hand side comes from. So let me give you a little bit more of the connection from the UVW representation of the algorithm to the algorithm that sort of makes sense to us. So here are the factor matrices. I'm going to write them in sort of a table form, and I'm going to label the rows and columns. Okay, so here's how it works. So there's 7 multiplies, and I have a column for every multiply. So look at, say, M4 over there, which is A22 times B21 minus B11. So M4, in this column of U, which corresponds to my A, I've got a 1 in the A22, and that means I just take A22 out. And then if I look in the 4th column of V, which corresponds to B, I get a minus 1, B11, we see that shows up, and then a B21 shows up. Okay, so then if I keep looking down the column, M4 is going to be used to compute C11, and it's going to be used to compute C21, and that's showing up there and there. Okay, so this is how the UVW matrices encode the algorithm. So if you have this representation, it doesn't seem hard to write the code for it. Okay, great. So now let me just write down the problem sort of in general, because it's not particular to 2 by 2 by 2 case, but we can do any dimensions. So if we have m by p times a p by n base case, then we get this problem, which I can write down in really short form. So I've got my tensor is specified, and I'm looking for u, v, and w matrices. And I just need to satisfy these constraints. It's just a set of trilinear polynomials. Okay, and so these constraints, this is just another way to write this equation. Okay, so that's easy enough to write down. In fact, if I find a rank R solution to this problem, then my omega naught pops out with this nice formula, and I can compare it to see how good the algorithm is. Okay, so I can write it down easily. It's not easy to solve, obviously. The problem's at the top again. Okay, so it's an NP complete, which you might expect. For a general T, I mean, this is just one tensor, and it's kind of simple, so that shouldn't slow us down too much. There's many ways to formulate the problem using combinatorial solvers and combinatorial search tools. But the most effective way that we found is to take a numerical approach. So there's lots of numerical ways to compute low rank approximations. We're looking for a decomposition, an exact decomposition, but we can get approximations pretty efficiently. And the typical approach is called alternating least squares, but there are some pitfalls. We're definitely not guaranteed success, and even if we have success, it doesn't give us an algorithm immediately. The important point is we want exact algorithms. We really want the entries to be from a discrete set, so like plus and minus 1 would be really nice, and we would like our answers to be as sparse as possible. Okay, so let me just give you a little more details, and maybe I'll go fast over this slide, but if you're interested, I'll talk to you more about the details. But this is how the most effective approach to finding the algorithms works. Alternating least squares says you solve for one of the factor matrices given the other two, and you just alternate over them. So there's sort of 3 steps to the inner iteration. Solve for u given w and v, solve for v given u and w, and so on. Okay, so there's funny notation again, but what I'll point out is this is a linear least squares problem. All these guys are matrices. And this is just a regularization term. Okay, so this is my regularization parameter. If I covered up u tilde, this is like using ridge regression, basically. So every inner iteration is really easy to solve. We use LAPACK to solve it. We can even use a communication avoiding QR algorithm if we want. But these are really small. But it takes many iterations to get anywhere, and I sort of mentioned the other pitfalls. And important point is there's a lot of art in picking the lambda and picking these kind of funny matrices that we put in the regularization term. So there's some art there which I won't go into. Okay, but we found a bunch of algorithms. Okay, so Strassens is.
How do you get rid of the approximations? And do you hope that the solution that you converge has 0 errors? Is that?
Yes, you hope. So it's in this.
Okay.
So you get something, maybe something gets small, and so you try to convince it to go to 0. And if it does, then maybe it convinces something else to go to 0, and then maybe you can get an integer out or a nice number instead of a weird floating point number. It's a lot of art.
Oh, so it's not automatic. You have to. Okay, fine.
Yeah. Okay, so and so this technique comes from Smirnoff. This is a very recent paper, and actually we were working on a very similar thing when he came out with this paper, and he was doing it a lot more successfully than we were, especially in picking these sort of special matrices. Okay, but we found a lot of algorithms. Okay, and these are, they could be practical. They're a small base case. And so this notation here, so Strassen is solving a 2 by 2 by 2 problem, and here's the 3 by 3 by 3 problem I told you about. But we don't need to square subproblems. We can cut things rectangularly. And so you can pick any 3 numbers, and that gives you a base case and look for the best solution you can find. So you can look at the rank. Sure.
I didn't catch what you just said.
Okay, so this notation over here, there are 3 parameters that tell you the size of the base case. So for Strassen, he cut things down by 2 by 2 matrix times a 2 by 2 matrix. And we also talked about 3 by 3 times 3 by 3. But you could use recursion, say 2 by 2 by 4. So cut the last dimension into fourths and cut the first 2 dimensions in half. and then you'll get another problem. And if you use so maybe there's an easier, well, if I use the classical algorithm here, and I do it recursively, then I end up doing 16 multiplies. But if I find a fast algorithm that's of rank 14, then my recursive algorithm will have 14 subcalls. So maybe
These are exact. These are
exact, yeah. So maybe let me skip. I'll come back to the previous slide. So here's an example with 4, 2, 4. So I take my matrices, no matter what their dimensions are, and I split according to those numbers. So I get a 4 by 2. These are not quadrants now, but this is n divided by 4 by n divided by 2 if I start with a square matrix.
So I should read it like 4 by 2 times 2 by 4.
Yes, exactly.
In all cases.
Yes.
Okay.
Okay.
Thanks.
Okay, so back to this table. So we can compare the number of classical multiplies for that particular base case to the ones we found. And sure.
So when you're searching for this minimum rank, you have two things. Either you don't know if your approximate solution, the iterative least or the alternating least squares found a solution at that rank, or that rank just doesn't have the solution, right? So are you iterating over rank as well?
Yes, but I mean, we have some idea of what rank we hope to get, and we spend a lot of time there. So for many of these, there actually are known lower bounds. So I told you that 3 by 3, there's a gap, but for most of these other ones, at least like here and above, and not 3 by 3, there's definitely a lower bound. The lower bounds are kind of spotty. So some of them have to take a certain shape, So, but there are definitely open questions here. But yeah, so you can spend a lot of time looking, and you'll never find it, and you don't know. Yeah. Okay. All right. So you can sort of compute quickly what your possible speed up could be if you implement this, and sort of additions are free. Just looking at multiplies, you can compute the exponent very quickly, and so all these are in the ballpark of Strassens. But I will point out that this row here is a new algorithm found by Smirnoff with the technique I showed. And so the base case is 3 by 3 by 6. It's an exact algorithm that gives you 2.77, which is an improvement. And this could be practical. These last two are sort of for comparison. The stars mean that they're approximate algorithms. So this first B is Beanie. He was the one that came up with that nice idea. Very small base case. This is Schoenhager, who was also on the plot, but this is a different paper where he came up with an approximate algorithm for 3, 3, 3. So these guys have better exponent than Strassen, but again, they're approximate algorithms. But we can implement them, and so we did, and to look at how fast they are, even if they're not that useful. Okay, so here's the example of 4, 2, 4, and the main idea here is that this is the structure of all these algorithms. You do some linear combinations according to your U matrix, some according to your V matrix. You make recursive calls, and then you do some linear combinations. And that's it. So we should be able to implement all these algorithms in the same way. Okay, so let me get to the practical performance. Okay, so they have the same structure, which I just showed you. So we can write a code generator to given a UVW matrix, translate it into code that we can run. Okay, so I had a student working with me this summer, and he got that part done. You can write correct code pretty quickly. But to get good performance, it takes the rest of the summer. So what do we have to worry about for performance? So basically, we're just doing multiplies and adds. I mean, these algorithms just generate some subproblems, which are multiplies. We'll use the library implementation for that. And to get to those subproblems, we need to do some adds. So it really matters the vendor library performance for the classical algorithm, because that's our base case that we'll use. It will matter the efficiency of our addition. So if we do that poorly, then we can just lose everything. And then we need to figure out when to switch from our fast to the classical algorithm. And then maybe I won't get to the parallelization that we use, so that brings in a new level of complexity too. Sure.
Is there any difference in numerical accuracy of these algorithms?
Yes. So I'm not going to talk about it, but yes, definitely. So, and actually there's theory. So given a UVW matrix, you can actually write down some theoretical bounds on the numerical accuracy. And so the numerical stability you get is not as good as the classical algorithm. But it's not that bad. I mean, these things aren't totally unstable. It's just that stability guarantees aren't as tight as the classical algorithm. But we didn't look at sort of empirically what things look like yet, and we want to. Okay, so all right, so I'm going to go into a few details about these, how to get good performance here. So the first is, what's the classical library performance? What does it look like? So here's this is square matrix multiply. Dimension here and performance up there. And this curve is very familiar for people who've dealt with DGEM. We're using Intel's MKL. And basically, there's a quick ramp up, and then you have basically flat performance, which is something like 90 or 95% of peak for classical multiply. So this is important. The shape of the curve is important, because what we're doing is we're going to sort of trade. We're going to say we're doing Strassen. We're going to do 7 multiplies, but it's half the size. So if we're sitting at n equals 3,000, and we want to use a step of Strassen, then we're going to have 7 subproblems of size 1,500. And if this performance is as good as this performance, then we should get the speed up that we expect, as long as we've done the additions correctly. And for big matrices, they shouldn't hurt too much. But if we want to go 1,500 to 750, well, then it's not clear if we can maintain that performance. Okay, so that gives you a little bit of a rule of thumb of how many steps you can take before you have to switch to classical. And if someone were to write better classical code and get a curve that sort of stays level longer, then we could run more steps of a fast algorithm. So if they could improve classical, it would actually help the fast as well. But they worked very hard to get this curve the way it is. So in the sequential case, it's very good. Actually, in the parallel case, it's much slower to get up there. The machine we were using had 24 cores, and it's hard to sort of parallelize small matrix multiply over 24 cores. But I guess the takeaway is that the shape of the performance curve matters a lot for our performance. Okay, so then what about additions? So maybe I won't spend too much time with this, but we basically looked at 3 different ways to do the additions. I'll tell you about the right once, which we saw had the best performance. You can do things like common subexpression elimination. So the UVW matrices come back at you, and they might have you do some additions multiple times. And so you can sort of account for that, create a temporary to do them only once. If you've heard of Winograd's variant of Strassen's algorithm, that's basically what he was doing.
So did you try using compiler techniques, automated techniques?
We did a simple automatic thing, which was just
fast Fourier transform library. They actually built a compiler for that.
Okay. So we thought about doing something smarter. It's just that it didn't help. So we got best performance with right once, and it can actually hurt the right once performance. It could help one of these other two, so it might be something to pursue, but we sort of started down that path, and then it wasn't helping, so we stopped. But yeah, we did a simple automatic thing that wasn't as sophisticated. Okay, so the right once is basically, so S are all the multiplicands that come from A, and for each one, you make sure that you only write those ones. So for every entry of S1, if it depends on A11, A12, and A22, then you sort of read in 3 streams and write out 1. Okay, so maybe I won't go into any more details there, but this is the approach that we found gave the best performance. So here's the performance curve for a bunch of fast algorithms. And so we could implement a lot of them. And the ones I showed you can do rotations, and so we got a bunch of algorithms. So this is obviously a bit of a mess. So let me clear out most of them so we can look at only a few. So the important ones are, this black one is the classical, that's MKL by itself. The black triangle one is Strassen, so we can compare against it. And then the red one that's getting the best performance, that's Beeny's algorithm, which is approximate. So it's not quite practical, but it's something that we can look at the performance of. And you see some of these others of the different shapes are kind of competitive with Strassen. Okay, so nothing is really beating Strassen. So this one actually gives a better exponent. It starts to be kind of competitive here, but it has a slow ramp up. So nothing too exciting. Strassen seems hard to beat in this case. So this is square matrix, 2 square matrices in the sequential case. Okay, so where we found something a little more interesting is if we have rectangular matrices. So suppose your matrix multiply looks more like this. This kind of looks like an outer product shape. Then it turns out Strassen isn't the best thing to do. So here's an experiment where we take the long dimension, the outer dimension, and make it big and keep this inner dimension fixed. And so that's the x-axis here. And then performance, the black triangles is again Strassen, and we see that we're beating Strassen now. The red curve is beating it, but that's approximate. but the light blue and the green are also beating Strassen. And if you look at those 424 and 323, they kind of fit the shape of this outer product. So we're going to divide the big dimension by 4 and the small dimension by 2 and the big dimension by 4. So they're matching the shape. And so a similar story for this other kind of shape where you have 2 small dimensions and 1 long dimension. And there, the dark blue curve, 433, sort of matches the shape. So there we can start to beat Strassen. Okay, and there aren't huge wins. So Strassen's beating classical by 10 to 15%, and we get maybe another 10% on top of that. Okay, but this is practically beating Strassen. And the exponents of square matrix multiply aren't as good as Strassen, but because they match the shape better, we get better performance. Okay, so let me maybe skip over the parallelization techniques. Basically, we had 3 ways to parallelize the algorithm. It's all about traversing the recursion tree in parallel. Okay, so if you've written parallel code for recursive algorithms before, there's kind of a BFS, breadth first search approach, and a DFS approach, and so we did both those, and we used a hybrid approach, which we assumed would do better sort of over greater ranges. And let me just show some performance here. Okay, so this is still a square matrix multiply. We're running on a machine that has 24 cores in 2 different Numa regions. And there's 2 groups of curves. So these bottom curves are with 24 cores. The performance is per core. And the top curves are over 6 threads. And so a couple takeaways. So one is that the 6-core performance, so the black is classical and the others are the different parallelization techniques we had. The performance looks pretty much like the sequential case. So if you just take the best of the colored compared to the black, then we're getting something like 20% win, like we saw in the sequential case. But for the 24 cores, we don't see that. And there's a reason for that. So we're doing multiplies and we're doing additions. And with the multiplies, we sort of need the multiplications to scale with the number of threads. And we kind of get that if we parallelize correctly. But with the additions, it's all bandwidth bound, memory bandwidth bound. And when you run with 1 thread on your node or run with 24 threads, the memory bandwidth difference is only like a factor of 5 or 6. So your memory bandwidth doesn't scale with a number of threads. And so that means your additions are going to be bound by a scaling factor of less than 6, whereas your computation, your multiply scaling happens at maybe closer to 24. Okay, so additions just become more of a bottleneck in that case. And there's not much we can do to get around it in shared memory. So with 6 cores, the multiplies and adds both scale about the same, so we see the same sort of relative performances in the sequential case. Okay, so I won't go into the rectangular cases, sort of a similar story. 6 threads is like sequential, 24 threads, we never really see a speed up over classical. Okay, so let me wrap up here. Okay, so in theory, we sort of saw that asymptotically, fast algorithms reduce both computation and communication. So that's kind of exciting. And in practice, Strassen's algorithm does well. It can beat the classical algorithm, the DGEM. But if we look at these other fast algorithms that we can find with the small base cases, Strassen's algorithm is hard to beat for square matrices. So we never really saw anything do better consistently. But for rectangular matrices, Strassen isn't the best. It's sort of tailored for square, and if you have algorithms that match the shape, then you can get better performance. Then we saw the shared memory parallelization has this bandwidth bottleneck that the additions start to cost too much. But we don't expect to see this in the distributed memory. And we haven't implemented all these algorithms there. And so there's more hope for these fast algorithms with big base cases. Okay, so some of the open questions. One is the question about numerical stability is still open. So theoretically, there are bounds, but empirically, we haven't looked yet. Looking at distributed memory is next on the list. And then, is it worth looking for bigger base cases? I'm not sure. So we implemented this algorithm that had the better exponent than Strassen, and it never really outperformed it. And so you have this overhead as the base case grows, the number of recursive steps you can take is limited, and the number of additions seems to be higher relative cost. So I'm not sure if it's worth looking for a lot of bigger base cases or not. I've gone back and forth on my pessimism and optimism. But the last one is, can we take this and put it into other applications? So other linear algebra algorithms can use matrix multiply. Are there some applications that could really benefit from this? And can we actually put it in and see speed ups there? Okay, so I'll end there. Thank you very much for coming. Sure.
So have you thought about, in the context of extending to other algorithms, like a lot of graph problems fit into this framework, but they have this additional constraint of sparsity, or some sort of structure on the graph which induces a structure in the matrix. Have you thought about extending these ideas?
Yes, yeah. So I'm sort of pessimistic about dealing with sparse matrices. I mean, so there's been some theoretical work sort of using some of the fast algorithms, especially the rectangular shaped. I don't know if they'll be practical though. And there's lots of papers that sort of reduce their problem to matrix multiply and then inherit the exponent, but I'm not sure how practical they are either. But yeah, it would be nice if some of the graph problems where things get dense enough that this could help, maybe it could help out.
Cool. So let's thank the speaker again.
Okay.